All right, let's look at enthalpy of formation. So this is the heat to form either a compound or element. So looking at energy, you got kinetic energy, energy of motion, or energy that's being transferred. Thermal energy is associated with temperature. It's just a form of kinetic energy. So we have reactions where things form. So reactions of their elements in their standard state, meaning how they're normally found, to form 1 mole of a pure compound. Now, standard state of an element, it doesn't take any energy to form the element. It naturally exists. The form in the appendix that has a heat of formation that's 0. So these would be things like metals, often as solids, many of our gases that we find are diatomic gases. Those are not only as like O2, N2, I2, all those things, but in their natural states. Coefficients of those reactions may be fractions, but often not the case, because the definition requires 1 mole of a compound to be made. Now, the formation of a reaction is very simplistic. It's from its basic elements, because carbon and oxygen, found normally, would make carbon monoxide as a gas. Now, again, we'd have it as O2. Carbon as a graphite has a heat of formation as 0. Diamond is a little bit higher. Oxygen is a regular state. So these would both be 0, and there'd be some energy released or absorbed to make carbon monoxide. The equation must be balanced, and really the product of the compound must be 1. This is where your fractions come in. The idea is that we're making both to where we have the product coefficient to be 1. Why 1? Because that's the way they made it. Now, we're often not going to be making these formation reactions. We're going to be utilizing these reactions. So what we're looking at is we're trying to determine the standard enthalpy change for a reaction. You remember a few lessons ago, we had enthalpy of reaction. This is where it comes from. Now, you can use bond energies. You can use this area, and then you can also use what's called Hess's law, which is upcoming. So any reaction can be written as the sum of formation reactions, or the reverse, again, because it can go either directions, as long as it's for the reactants and products. So the change in enthalpy for a reaction is the sum of this heat of formation for the components. So we're adding up all of the heats of formation for the products with their coefficients, minus all of the heats of formation for the reactants with their coefficients, individualized. So for example, you've got CH4, O2, CO2, H2O, products minus reactants. We've only have 1 CO2, so C, no coefficients, 2 water molecules, so we have a 2 here. 1 of the CH4s, 2 of the oxygen. I always recommend writing the coefficients, even if it's 0, to illustrate that you understand there are 2 moles of that 0 heat of formation oxygen. Adding those all up, you get a negative delta H of reaction, a very exothermic reaction, which makes sense. When you burn methane, you get heat. Now, a little bit different this time. Same reaction overall, but we're going through the ideas of different components going on here. Now, this is just showing another energy diagram, breaking it down. We go from methane and oxygen to breaking it down to carbon and our constituent elements. Take some energy to break those bonds. Forming CO2, then forming water. So all in all, we're still using the same ideas here, but we see we get a different value. Now you might say, what's that about? Well, do you see anything about the numbers? They can vary slightly based upon the appendix used. They're always going to be based upon some interpretive values. Always use the numbers given to you. Otherwise, look them up and don't stress if it's not exactly the same. So keep that in mind. However, water was a gas in one and another was a liquid. Phase matters. So let's take a look back. Gaseous, right up here. Liquid, right here. This makes sense that phase matters because it takes more energy to make it a gaseous form than it does a liquid form. For combustion reactions, I've seen many that are liquid and many that are gaseous. follow what it says, and be careful that you do choose the right value. So let's take an example here. Ethanol used in many fuels. What's the combustion of ethanol? Right, so we got our values all given to us. So that makes it nice to enough to get confused about something, although they do give it as a gas and a liquid. So make sure you're aware of that. One thing you can also note, they don't give you O2. So even if you forgot that O2 is 0, kind of prompts you to think that anyways in this case. Again, products minus reactants, 4 carbon dioxide plus the 6 water as a liquid, correct? Minus 2 of the ethanol plus 6 of the oxygen, we see that there's a large amount, and make sure you get your signs correct. Always watch your negatives. Be careful to use your parentheses on your calculator or do it in stages. Always just be cautious that you're aware of those mathematical things. Not much else to it. Again, following, making sure you get all the things straight up, and making sure you know these comfortable enough for speed. All right? Let me know what questions you have. Take care.